So the first content for the leftover is called solution. Solution. So one, we talk about the aqueous solution, right? Aqueous solution. So when we write the state is AQ. So what exactly is a solution mean? It's just that we have some solids or some other stuff. They dissolve in or liquid. They dissolve in the water, and then they are making a mixture. And this mixture is water combined with some of the substance. Okay, so that's called a solution. So when we talk about a solution, and generally is involving three concepts. One is called a solute. One is called a solvent. The other one is called a solution. So solute is the one that dissolved in the water. It's a substance that is dissolved in the water. So that is the solute. And the solvent over here, well, it's just a water. Okay, this is what we call solvent. And the solution is just the solute plus solvent. So this is generally is a definition: solute, solvent, and the solution. So when we talk about, for example, we talk about sodium chloride solution, then they give us a hint. That means sodium chloride is a solute. And the water is solvent. And sodium chloride plus water are solution. Is solution. Those two add together is solution. So in general, when we talk about solution, we're not talking about water, right? We only talk about the solute, right? Because we assume those are dissolved in the water. So we're not mention what kind of the solvent it is. We just talk about what the solute it is. Like a sodium chloride solution, or talk about the barium, copper 2 sulfate solution, or even sugar solution, right? So we only talk about solute. We're not talking about the solvent. Because we only just care about the solute. We generally don't care about too much about the solvent. So since we care about the solute, and then we are going to introduce another concept. It's called the concentration. Anyone know what is the definition? I mean, general, in your word, what is the definition for concentration? Please.
Would be the ratio of solvent and the solvate.
Yeah, the concentration, there's a lot of way to represent the concentration, but generally it just talk about how heavy or how strong the solute, or how much the solute that inside of the solution, right? In the particular unit. Okay, so that is what we call a concentration, right? You're making a lemonade. Your fuel is too sweet, right? Too sweet, that means it's too high on concentration of the sugar in the solution. So that is just a concentration, right? So when we talk about it, there's a different way to talk about concentration. We can using percentage, just like when you drink the alcohol, you will see what is the percentage of the alcohol in there. Anyone knows what is the percentage for the alcohol in the beer? 8%. That's too strong. Okay.
4.2.
you're good.
Alcohol.
4 to 5, that's normal. Okay, yeah, but I did drink one of this is a 6.5. Yeah, that's pretty strong. Okay, it's already strong enough. That's for beer. How about wine?
That's what wine.
11
or 10 to 12. This is generally the range. That's in percentage. So what is the percentage? That's just how much alcohol divided by how much the volume of the alcohol divided by the volume of the water. So that is a percentage. Okay, yeah. So do you know what is a Volga?
40.
40, more than 40 actually.
Oh, really?
Yeah,
Oh,
yeah.
40.
I think the highest one is above 56.
I also saw the 46 something. Okay, for the Volga. Okay, I mean you can also get like a 90. It's almost like just the medical alcohol. Okay, yeah. So anyway, that is the concentration. This is also concentration, but in here, Chem 1, we're not using that concentration. We're using another way to represent the concentration. It's called the molarity. It's called the molarity. So the molarity is also very common in chemistry and for the represent a concentration. So in the Chem 1, if we talk about concentration, generally talk about the molarity. If we talk about molarity, then you need to recognize we're talking about concentration. Are you clear? Okay, yeah. So molarity, by definition, over here is how much mole of the solute divided by liter or volume of solution. Okay, yeah. So molarity, and just molarity, the people using capital M to represent. Okay, usually for the
Unit is a capital M. But if you're looking at the unit over here, mole over liter, right? So mole over liter is also the unit for molarity. So in general, the capital M is mole per liter. So we call the capital M here is called a molar. It's called a molar. Okay, yeah. So capital M is just a mole per liter. Are you clear? The mole per liter. So for example, if we have a 0.5 mole of the sodium chloride, dissolved into like a 0.25 liter of the solution. And what's the concentration? What's the molarity? What is the molarity? And in general, the molarity is just equal to, again, mole of the solute, which is a 0.5 mole of the sodium chloride, divided by liter of the solution, which is a 0.25 liter of the solution. And then you will got the molarity, 0.5 divided by 0.25, then you got 2.0, then capital M, or the unit mole per liter. Those are the same unit, okay? Those are the same unit. Capital M equal to mole per liter. That makes sense, right? So we have a 2.0 mole of the sodium chloride. That is already pretty high for the concentration. That's pretty salty, I think. This is should be very salty. Okay, but when you're do the concentration, you see we're using mole over liter. We're not using gram or not using mass, right? So when you see the mass, for example, if I have a 0.30 gram of the sodium chloride, that is dissolves into 500 milliliter of solution, then how do we figure out the molarity? Again, by definition, you have a mole over volume, right? You got a mole over volume. So in this case, you need to convert that to the mole first, and then you divide by volume, which is a liter of the solution, okay? Mole over liter, mole over liter. So this is a milliliter. So first thing, convert that to liter, and this is 0.5 liter. Okay, let me just put a dot up there. So we're going to have a milliliter. So we're going to convert that to liter. And this is a gram. So you're going to do two things. Convert a milliliter to liter. The volume become liter. And then mass to the molar mass. The mass to the gram. Mass to the mole. Okay. Mole of the sodium chloride, that's equal to mass over molar mass. Mass over molar mass. The molar mass of sodium chloride is 23.0 gram per mole and plus 35.45 gram per mole. Then you will find the mole of the sodium chloride. (23 plus 35.45) 0.005133. 0.005133. And once again, please do not round those numbers too much when you're figure out the mole, because that's not a final answer. We're not going to round. We're going to keep the enough sig fig and then going to round at the very end. Okay, because the question asking for molarity is not asking for mole. So we got a moles of sodium hydroxide. By definition, the molarity is equal to mole of the sodium hydroxide divided by the liter of the solution. So mole of sodium hydroxide is just 0.005133 mole, and divided by liter of the solution, which is 0.5000 liter. And then you will get an answer. Point 0.0103. 0.010266. And this is a capital M, molarity. That's concentration. And then here, since the answer, if you look at sig fig, this is 2 sig fig, and this is like a 4 sig fig. So we're going to keep 2 sig fig. So the final answer will be just 1 and 2. And looking at the next one is 2. So the answer is just 0.010 molar. That's it. Okay, yeah. One thing I need to mention carefully around here is the molarity. Is not equal to mole. Those are two different concepts. Molarity is still talking about how many moles of the solute in the solution. But that's talk about how many moles of the solute in 1 liter of the solution. But this mole is just talk about how many molecules numbers in the solution. I mean, there's no limit on the unit of volume. Give you one of the example and talk about what that means. We have a 0.5 mole of the sodium chloride. And then we put that into 0.5 liter of the solution. And we're going to using, we're going to put 0.5 mole of the sodium chloride and put into 1 liter of the solution. And if you're those put into the solution, then what happened? Will the mole change? Will the mole of the how many volume, how many numbers of molecule of sodium chloride in the solution, is it changing? It's not changing, right? Left side, we put 0.5 moles of the sodium chloride. Right side, we also put 0.5 moles of sodium chloride. So generally, how many number of the sodium chloride that we put into the solution is the same. But the left one is more salty because they have a higher concentration, which means they have a certain unit of the sodium moles of sodium chloride is higher than this. So the molarity, the concentration on the left side is stronger than the on the right side. The molarity on the left side is 0.5 mole over 0.5 liter. So that's a 1 mole per liter. On the right side, it's just 0.5 divided by 1 liter. Then you got a 0.5 molar. So left side has a stronger taste than the right side. But the total numbers of the molecules is not changing. Are you clear? Does it make sense, right? So molarity is not equal to mole. Don't just looking at 0.5 molar and you know, oh, this is 0.5 mole. No, this is completely not right. Okay, let's talk about concentration. You need to, that really depends on how many volume of the solution you have. Then you can figure out how many moles of that. Make sense, right? Yeah. Or you can think about, okay, we have a 2 tank. And this tank has a 5 liter of solution. And we have a 0.05 molar of the solution, sodium chloride in there. And the other one, we have a 0.2 molar of the sodium chloride, but we only have a 0.5 liter of the solution. Then which one has a higher mole of the molecules? Which one has a higher moles of the molecules? Then how do we compare? And remember, that's a constant. So that's why we talk about concentration. It's just talk about how strong the solute in there. It really doesn't affect the, you're based on the number over here, you cannot tell which one has the higher numbers of the sodium chloride molecules. That's really depends on the volume you have, okay? Then what we do, molarity is equal to mole over volume. Molarity is mole over volume. So 0.05 molar is just this. If you multiply the volume, you see volume and volume canceled. Now you got a 0.25 mole of the sodium chloride. This is how you figure out how many moles of that, which is using molarity and you time volume. Okay, molarity time volume, you got this. Okay, molarity time volume, then you got mole. Molarity time volume, you got a mole. On the right side, you have a molarity, which is 0.2 mole. Obviously, is stronger than the left side, but they have a really small amount of the solution. They only have a 0.5 liter. So this is, again, this is a mole per liter. So you see liter and liter canceled. Now you only have a 0.1 mole of the solution. You have a 0.1 moles of sodium chloride. Again, mole, that's equal to molarity time volume. Mole equal to molarity time volume. So you see, on the left side, we have a less concentration, but we do have a higher mole. That's because we have a really large amount of the water, the solutions of there. But on the right side, we have a higher concentration, but we have a less volume, so make the moles of sodium chloride get less. So that's why I want you to be clear about the molarity is not equal to mole. That's a totally different concept. Mole is talk about how many molecules there, and molarity is talk about how many molecules in a certain unit of the volume. Make sense? Make sense? Okay, so another concept related to this is if we talk about, for example, if we talk about sodium chloride solution, if we have a 0.5 molar of the sodium chloride solution, and you generally can figure out what is the, and we know this sodium chloride solution, right? This is electrolyzed. So when they dissolve in the water, that should be sodium ion and a chloride ion, right? So you can also just based on the concentration of the solution to figure out what is the concentration for each of the ions. 0.5 moles of the sodium chloride solution will have a 0.5 moles of sodium ion in the solution, and also 0.5 moles of the molar of the sodium chloride ions in the solution. That's because 1 mole of the sodium chloride actually can make 1 mole of the sodium ions plus 1 mole of the chloride ions. Make sense, right? So you can just looking at the ratio or the numbers of each of the ions, and then figure out to predict what is the concentration. Or for example, if you want to, you have a 0.1 molar of the potassium sulfate solution, then what is the concentration of sodium potassium ion? What is the concentration of the sulfate ion? Again, you still can predict that just based on the concentration shows over here. If you're looking at here, in this compound, we have 2 potassium ions. 1 mole of the potassium sulfate has 2 potassium ion. So that means the concentration of this is just 0.1 molar. For the solution, you multiply by 2, which is 0.2 molar for the sodium chloride, potassium ion. And what is the concentration for the sulfate ion? Then you're looking at how many sulfate in this compound. We only have 1 sulfate in this compound. So the concentration of sulfate is just 0.1 molar, your time 1, which is 0.1 molar, the concentration. Make sense? Okay. Then how about what is the concentration if we have a 0.5 molar of the aluminum chloride? What is the concentration of the aluminum ion? And what is the concentration for the chloride ion? And generally, you do the same thing. Just looking, go ahead to think about it. What is the concentration for the aluminum ion? What is the concentration for the chloride ion? That's pretty straightforward, right? Aluminum ion, since how many aluminum in this compound? 1. So the concentration is just 0.5 molar. You time 1, you have 0.5 molar. So that's it. How many concentration for the chloride? And then that's 3 of the chloride in this compound. That means 0.5 molar, you time 3. So you got 1.5 molar for the concentration of chloride. That makes sense? Tyler, do you have a question? Okay. So generally, this is pretty much I'm going to talk about for the solutions. Okay, we know how to figure out the solution, and also by definition, mole over the volume, and how to based on the solution to figure out the concentration of the solution to figure out the concentration of the ion inside of solutions. Okay. The last part I'm going to talk about, that's gonna be still talk about empirical formula, but that's is an empirical formula from a combustion reaction. empirical formula from a combustion reactions. So, for example, when we talk about combustion reactions, we only talk about the one simple case, which is the hydrocarbon. The hydrocarbon react with oxygen, then they are going to produce water and CO2. So this is only one case we talk about. I know for combustion reaction, I mean, this is a carbohydrate. Carbohydrate can also making the combustion reaction, but we're not talking about these cases, which means, you see, all the oxygen is coming from, all the oxygen in this product is coming from the oxygen, and hydrogen is coming from the hydrocarbon. Carbon is also coming from the hydrocarbon, right? So in this case, we try to figure out what is the empirical formula for this hydrocarbon. Okay, so again, you want to find out the empirical formula for the hydrocarbon, then you just need to find what is the moles of carbon, right? And what is the moles of hydrogen. And then you got the moles of carbon versus moles of hydrogen, and then you try to make this as a whole number, and then you can figure out the ratio between carbon and hydrogen. That makes sense, right? This is generally what we do for all the empirical formula. But here is a little bit variation, is because now we're not having moles of hydrogen and moles of carbon. We have a moles of water and moles of CO2, right? The question usually will give you, okay, how many moles, how many gram of the water and how many gram of the CO2, and then you try to figure out the answer. So let's looking at one of the question in the page number 6. The page number 6, question number 1. Okay, page number 6, question number 1. Page number 6, question number 1. Page number 6, question number 1. Okay, so this one, they talk about, we have 122.3 milligram of the compound A. Undergo complete combustion to produce 421.7 milligram of the CO2 and 64.7 milligram of the water. So here, 122.3 milligram didn't do anything over here. It didn't do anything, okay? We just need to know the mass of the CO2 and the mass of water, that's it. Okay, yeah, because, so here, let's see. The mass of the water, CO2 is 421.7 milligram. And the water is 64.7 milligram. So we have the mass of the water and the mass of the CO2. So obviously, first we need to convert that to gram, right? Divided by 1,000 to got a gram. So that's a 0.0647 gram. And this is 0.4217 gram. So we got a gram, then we need to convert that to mole, right? Because we need to find a mole of the carbon and hydrogen elements. But remember, this is the mole, this is a water, and this is CO2. So we're not going to just using this to divide by 1 gram per mole for hydrogen, because this is a mass of water. So you need to divide by the molar mass of water to get mole of water. That makes sense, right? Yeah. So you convert that to mole of water. Mole of water, then that's just equal to 0.0647 gram divided by molar mass of water, which is 18.00 gram per mole of the water. And this one is the same thing. You try to find a mole of CO2. Then that's going to be 0.4217 gram and divided by molar mass of CO2. Okay, because we're looking for CO2. So don't divide by 12 to get carbon. because this is the mass of the CO2. So we need to divide by molar mass of CO2, so we can get a mole of the CO2, which is 44.01 gram per mole for the CO2. And then we can, based on this, to figure out a mole of the CO2 and moles of water. Point 0.0647 divided by 18, you got a 0.003594. And that is a mole of the water. Remember, very important. That's a mole of water. CO2, 0.4217 divided by 44.01. You got 0.009582. 0.009582, and that's gonna be mole of the CO2. Okay, so now we got the moles of the water, and then we got the moles of CO2. Remember, what is the purpose for this case? The purpose, again, we try to find the moles of carbon versus mole of the hydrogen. That is the key, okay? But what we have a moles of water and moles of CO2. So now, then that's gonna be the case. How can we convert moles of the water to mole of the hydrogen? How to convert the moles of the CO2 to moles of the carbon? That's going to be the key. Well, if you're confused, then let's just think about it. If we have 1 moles of CO2, how many moles of the carbon that we can have for the 1 moles of CO2? Remember, that's atom. It just talk about atom. 1 moles of CO2, how many moles of carbon that we can find from the 1 moles of CO2? No idea? Just 1. Looking at the formula, how many of the carbon atoms in this formula? Just 1, right? So in this we are going to have 1 mole of the carbon. How many oxygen that we can find from this 1 mole of this CO2? 2, right? So that's the 2 moles of the oxygen. And this is also how you got the how you figure out the molar mass, right? You got a 1 carbon plus 2 moles of oxygen, then you got a molar mass. That makes sense, right? So now, if we have a 0.5 moles of the CO2, how many carbon that we have? It's just a 0.5 moles of the carbon, right? And you can also have a 1 mole of the oxygen, because that's just a 1 times 0.5, you got a 1.5 moles of carbon. 2 times 0.5, you got a 1 moles of oxygen. That makes sense, right? So that's why that's the same thing over here. Moles of CO2 convert to moles of carbon. It's the same thing, because 1 mole of the CO2 has a 1 mole of carbon. So if you have a moles of the CO2, you're gonna have the same moles of the carbon. And this is also another way for the stoichiometry, right? 1 mole, 1-to-1 ratio. 1 CO2 has a 1 carbon. That's a 1-to-1 ratio, right? So if you have a moles of the CO2, you're going to have the same moles of the carbon. That makes sense? Gentlemen, that makes sense? Right? So that's why if you have the moles of CO2, now you can have the same moles of the, since you got the moles of CO2, now you're going to have the same moles of the carbon. I try to let you understand, okay, why we can got this, okay? I don't want just let you follow the steps. What if we have something confused, and then you're totally lost? So we need to know, okay, once you got the moles of CO2, you can figure out the moles of carbon, and the moles of carbon is what we need. Because when we figure out the empirical formula, we need to get the moles of carbon. And same thing for the moles of water. But here is a little bit different because that's a H2O for hydrogen. 1 mole of the water, if we have 1 mole of water, how many hydrogen atoms in there? You got 2 moles of the hydrogen atoms. Make sense, right? Because this is a 1:2 ratios. 1 mole of water has 2 moles of hydrogen atoms. So that is why if you got moles of water, you need to time 2 to get moles of water, hydrogen. Make sense? Kiara? Do you have any question? So that is why when you got the moles of the hydrogen over here, you need to time 2. Then you got moles of the hydrogen. And this is mole of water, then you time 2, you got the moles of hydrogen. 0.003594 times 2. Then you got 0.007188. That is a mole of hydrogen. So remember, we really just need to get moles of hydrogen and moles of carbon. Then we figure out the ratios. Okay, so carbon versus hydrogen is 0.007, 0.009582 moles versus 0.007188 moles. And how do we do this? How do we do to make a whole number between the two ratios?
Divide by the smallest number.
Divided by the smallest number, right? Then one of this is gonna be a 1. Then the other one gonna be the number that's bigger than 1. Okay, yeah. So this one is the smallest. So we're going to divide by 0.007188. 0.007188. In this case, this on the right side, hydrogen is 1 now. And if you're looking at here, this is 0.9582 divided by 0.07188. Then you got 0.009582 divided by 0.007188. And you got 1.333. 1.333. And then what we do? Did you remember the rule? If you have a 0.5, you time 2 for the whole ratio, right? If you have a 0.25 and 0.75, you time 4. And if you have a 0.333 and you time 3, right? So because 0.333 generally is a 1/3. So 1/3 times 3, that's 1. So you got this ratio and you times 3, then this is going to be equal to 4 over 3. So you talk about empirical formula between the carbon and hydrogen, it's just a C4H3, and that's it, C4H3. So this is generally how we figure out the empirical formula for these cases. Well, in general, almost the same. The only difference is you need to find the moles of water and moles of carbon and moles of CO2. And based on moles of water and based on CO2, moles of CO2 to figure out the moles of hydrogen and moles of carbon. Okay, then you can using that ratio to figure out the answer. That's it. Are you clear? So this is the only thing that you need to care about. Pay attention on. All right, so we're done for today's lectures, and then let's just take a break, and then we will work on our practice.